In this video, we will explain how to use elementary matrices to compute the inverse of a matrix. If we have a square matrix, let's suppose that A is an n by n matrix, and let's suppose that A is non-singular. Remember that non-singular means that the null of A is just the zero vector, or also it means that A is row equivalent to the identity matrix. Then for a matrix that is non-singular, we can show that there is a matrix B, also n by n, such that B times A is the identity matrix. And also, once we have this relation, then we also have the A times B is the identity matrix. Then, given a matrix A, which is non-singular, we're going to find this matrix B that is called the inverse. B is called the inverse of A, and it is denoted by A inverse. And the reason is that this identity matrix makes the role of a 1. Notice that if we have any matrix C, n by n, times the identity matrix, give us C. And like in the same way, like any number x times 1, give us the number x. Then when we have like 5, and 5 inverse is the number such that multiplied with 5 give us a 1. 5 inverse is 1/5, and for that reason the matrix B that satisfies that B times A is the identity, the number that satisfies that 5 times that number is 1, is denoted by 5 inverse. This matrix B is denoted by A inverse. Then in this case B is denoted by A inverse. And that inverse only exists if the matrix is non-singular. Maybe to compare, notice that 0 doesn't have an inverse multiplicative inverse, because no number multiplied by 0 will give us 1. Here we can check that if you have a singular matrix, then no matrix multiplied by that matrix will give us the identity matrix. Let's do an example. Let's suppose that we have the matrix A equal 1, 3, 0, 4. Then let's do row reduction, and let's take it to the identity, but let's keep track of those changes. Let me here, let's do 1/4 of R2, and that will give us the matrix 1, 3, 0, 1. That means that the matrix A multiply on the left by the matrix E2 1/4 is equal to this matrix. Now let's do another change. Let's change row 1 by adding -3 times row 2. Then I'm going to change row 1 by adding -3 times row 2. And then we get the matrix 1, 0, 0, 1. And that means that this matrix is equal to this matrix multiplied by the elementary matrix. We are changing row 1, and by adding -3 times row 2. Then this means that the matrix A multiplied by this matrix, but this matrix is the matrix 1, 0, 0, 1/4. And this matrix here is the matrix row 1 changes, and row 1 is 1 minus 3 times row 2, and this is just 0, 1. And therefore, the product of these two matrices is a B, and it has the property that B times A is the identity matrix. Let's see what is the B. B would be equal to 1, negative 3, 0, 1 times 1, 0, 0, 1 quarter. And this is the matrix 1, negative 3 quarters, 0, and 1 quarter. And we can explicitly check that if we multiply this matrix 1, negative 3 quarters, 0, 1 quarter times the matrix A, which is 1, 3, 0, 4, then we get 1 plus 0 is 1. Here we have 3 minus 3 quarters times 4 minus 3 is 0. We get 0 and we get 1. Therefore, in this case, we have found explicitly the inverse of this matrix. We can say that A inverse is the matrix B, which is equal to 1, negative 3 quarters, 0, and 1 quarter. There are going to be a lot of more efficient ways to compute the inverse of a 2 by 2 matrix, or in general, but this is just a good exercise to visualize that every row operation can be viewed as multiplication on the left by an elementary matrix. Let's do another example. Let's consider the matrix A equal to, let's say, 1, 0, 2, negative 1, 0, 4, 0, 2, 1. And let's find the inverse. Then let's do row reduction. I can't put a 1 here, a 0 here, and I can do that by changing row 2 by adding row 1, and then I get the matrix 1, 0, 2, 0, 0, 6, and 0, 2, 1. That means that this matrix is equal to A times the matrix E2, 1, two, 1, 1. Let's keep going. Here we can change row 2 and row 3. And then we will get the matrix 1, 0, 2, 0, 2, 1, 0, 0, 6. And that means that this matrix is equal to this matrix, which is this one, times the matrix, the elementary matrix E2, 3. And then we can multiply by 1/2 row 2. And we have 1, 0, 2, 0, 1, 1/2, and 0, 0, 6. And then that means that this matrix is equal to this matrix times E2 of 1/2. And we can put a 1 here. And then this is 1/6 of R3. We can accomplish that by doing 1/6 of R3. And then we get 1, 0, 2, 0, 1, 1/2, and 0, 0, 1. And this matrix is equal to this matrix times E3 of 1/6. And now we can do 2 row operations. I can change row 2 by adding negative 1/2 row 3, and I can change row 1 by adding -2 times row 3. When we do these two operations, we get the 1, 0, 1, 0, 1, 0, 0, 0, 1. In this case, we can check that it doesn't matter what order we do these two, we will get the same answer. Then I will just do this one first, which is E. We're changing row 2, then 2, 3. And we are multiplying row 3 by -1/2. And this is, the other one is E. We are changing row 1 using row 3, and we are multiplying row 3 by -2. Then let's write down these matrices. E23, sorry, this E121. We are changing the second row by adding row 1. Then this is 1, 1, 0, 0, 0, 1, 1, 0, 0. Let's do E23. We're changing two rows, the 2 and the third, the second and the third. Then we have 0, 0, 1, 0, 1, 0, 1, 0, 0. This is E2 1/2. This is the matrix 0, 1/2, 0, 0, 0, 1, 1, 0, 0. And this matrix here, we're multiplying row 3 by 1/6. That means that the matrix is 0, 0, 1, 6, 0, 1, 0, 1, 0, 0. This matrix is the matrix we're changing row 2 by using row 3. Then here we have this, and -1/2. Row 3 is just the row 3 is just E3, and the row 1 is just E1. Finally here, we are changing row 1 by adding -2 times row 3, and the second row is just E2, and the third row is just E1. Let's do the product of these matrices. When we multiply these two, what do we get? Maybe we will need more space. I'm going to erase this part, and I'm going to just leave the matrix A. When I multiply these two, I get 1, 0, and here we get -2, 0, 1, -1/2, 0, 0, 1, times, let's multiply these two. When we multiply these two, I get 1, 0, 0, 0, 1/2, 0, and here we get 0, 0, 1, 6. I multiply these two, and now when I multiply these two, I get the matrix 1, 0, 0. I get the matrix 0, 1, 1. Sorry, 0, 0, 1, and 1, 1, 0. And we know that all of these times A give us the identity matrix. All of these times A give us the identity matrix. Let's do the product of these two. The product of these two would be 1, 0. Here we have 0 plus 0 minus 1/3. Here we get 0. We get 1/2. And here we have -1/12. And here we have 0, 0, 1, 6. And then times this matrix 1, 0, 0, 0, 0, 1, 1, 1, 0. And we know that this times A give us the identity. That means that the product of these two will give us the inverse. Then B equal A inverse is just the product of these two. Let's see, we have 1 minus 1/3 is 2/3. Here we have just negative 1/3. And here we have 0. Here we have negative 1/12. Negative 1/12. And we get 1/2 here. Now for this we get 1/6, 1/6, and 0. Then this is the inverse. Let's check if this is true. Also, if we have 2/3, negative 1/3, 0, negative 1/12, negative 1/12, 1/2, 1/6, 1/6, and 0 times the matrix 1, 0, 2, negative 1, 0, 4, 0, 2, 1. This is supposed to be the identity matrix. Then here we have 2/3 plus 1/3 is equal to 1. Here we have 0 plus 0 plus 0 is 0. And here we have 4/3 minus 4/3 plus 0 is 0. For this one we have negative 1/12 plus 1/12 plus 0 is 0. Here we have 0 plus 0 plus 1/2 times 2 is 1. And here we have negative 2/12 minus 4/12, negative 2/12 minus 4/12 plus 1/2. What is this? This is negative 6/12 plus 1/2, but negative 6/12 is negative 1/2 plus 1/2 is 0. And finally here we have 1/6 minus 1/6 is 0. And you have 0 plus 0 plus 0 is 0. And here we have 2/6 plus 4/6 plus 0. That's 6/6, which is 1. Then we have shown that this matrix has the property that B times A is the identity matrix, and for that reason B is the inverse of A. And essentially what we have done row reduction, but we have kept track of all the elementary matrices, and then at the end we get that A times a bunch of elementary matrices is equal to the identity. Then the product of these matrices is going to be B, which is the inverse of A. Remember that something important that we are using is that the product of matrices is associative, but it is not commutative.